Welcome. In this video, I'm going to go over two of the three rules for naming organic compounds, or what is commonly called nomenclature. So the IUPAC, the International Union of Pure and Applied Chemistry, is considered the international authority on naming chemicals, especially organic chemicals. So for organic compounds, it's really important to know the functional group as well as the size of the backbone or the stem of the molecule. And then a third thing important to know is if there's any substitutions for the hydrogens. Has another functional group been substituted? Has a halogen been substituted, or their branches? So because there's multiple ways to draw the same molecule, say a straight chain of 5 carbons or a branch chain, 1 branch, 2 branches, we have to have 3 different rules. So the 3 different rules are going to attack it in that order. What's the stem or the longest carbon chain? What's the functional group, and then what are any branches or substitutions? So rule number 1, find the longest straight or continuous chain of carbon called the backbone or the stem, or just abbreviated R, and don't let kinks or turns fool you. Like in the example below, these are all straight chains of 5 carbon, because if I take my pen and I start on 1 carbon, I can follow to all 5 carbons without lifting my pen up to follow a branch. So these would all be considered pentane stems. Whereas if I'd had it written like so, now when I try and follow all the carbons, I can get 4, or I can get 4, but I can't get all 5 without lifting my pen up to make that last branch. So that's the difference between a straight chain and a branch. So continuous doesn't mean they're connected at 180-degree angles, but that they're connected, they're bonded to each other, one alongside the other. So this determines the beginning of the suffix. See, I have an extra G there, or what I tend to call the stem of your name. Meth, eth, prop, but. Those 4 are kind of hard because those aren't prefixes or roots we're familiar with. So I remember it as mice eat peanut butter. And then when you get to 5, it kind of follows what you know in math: pent, hex, hept, oct, non, and dec. And really, much beyond hexane, we won't see a whole lot in this beginning organic chem unit. So then rule number 2 is all about the functional group. And this is where the work comes in, because there's a lot of functional groups, and we're only looking at some of them here. And I know it looks like a lot, and it is, but there is a method to the madness here. So just real quickly, if you look down the names, some of them make sense. Alkanes, you change you add the suffix to the name methane. Alkene, it's methene. Alkyne, it's methine. Alcohol, methanol. Ethers, there's an oxy in the middle. That's because there's an oxygen between 2 carbon groups. Aldehyde, it becomes methanol. And I always have a hard time pronouncing it, so it sounds different than the alcohol, but it's OL versus AL. So that comes from the beginning of the aldehyde name. Ketone, again, the name makes sense because it becomes ethanone. The name's right in it. And carboxylic acid, methanoic acid. Esters, methanoate doesn't seem to make a lot of sense, but again, it's because the functional group is between 2 R groups. And then the amide, amine, nitriles, and arenes seem to fit with the root, being similar to the functional group, or the functional group's name being similar to the family name. So most of the compounds mimic the name. The 2 that really don't are the esters and the ethers, because of the functional group being trapped between 2 R groups. And so you have to distinguish what the 2 R groups are. So some hints for determining your functional groups. You have to memorize them, but there is, like I said, there is a pattern and some similarities among them. So functional groups are usually one of 3. It's the bond with carbon that varies from a single to a double to a triple bond, or even a ring of carbons in the case of the arenes. Or the functional groups involve oxygen, either OH as hydroxyl, or oxygen single or double bonded to a carbon. And then the third group of functional groups that we're dealing with are nitrogen bonded to carbon. And it could be nitrogen just NH2. It could be nitrogen triple bonded to carbon by itself, or it could be nitrogen NH2 along with a double bonded oxygen. So given a structural diagram or formula, you should be able to identify the functional group and name the compound. And there's a very good chart on 314 that you might want to keep handy. And also know that in your data booklet, there's a lot of names and formulas. So if you can't remember exactly how to name an ether, for example, you can probably find an example of an ether and remind yourself of what the rules are. So use your data booklet as a resource for organic compounds. So let's start with the functional groups with different carbon-carbon bonds. The hydrocarbon family is when you have just carbon and hydrogen, so all four of these families are hydrocarbons. And in the alkane, it's a hydrocarbon that's said to be saturated. There's all single bonds between the carbons, and then obviously just a single bond between the carbon and hydrogens. The alkenes and alkynes are unsaturated hydrocarbons because there's at least one multiple carbon bond. So with an alkene, there's at least one double bond, and with an alkyne, there's at least one triple bond. And in fact, if there's two double bonds, we call it a diene. If there were three double bonds, we'd call it a triene. And then the same thing with the alkyne, a diene or a triene, to show that there's two or three of those triple bonds. We're just going to deal with one double bond in an alkene and one triple bond in an alkyne. So one thing I'd use to remember these three hydrocarbons is that the vowel at the end changes from A to E to Y, and that goes in alphabetical order with single, double, and triple bond. The arenes are the cyclical or ring structure, and it's always a 6-carbon atom ring, although there are 5-carbon atom rings, but the one we're going to be concerned about is the arenes, which are 6, and it's a variation off of a chemical called benzene. So it's 6 carbon atoms, which is often depicted as being alternating double and single bonds, but actually they resonate positions or they're delocalized, so you can think of each one as being a bond and a half. So all 6 carbons bond with just one hydrogen, so the formula is C6H6. But when one of those hydrogen gets substituted with something else, then it's considered a phenyl functional group or an arene instead of benzene. So what about the functional groups with hydroxy and oxygen bonded to it? Well, the OH group is going to single bond to a carbon because the O is going to single bond to the H on one side, and then it has a bond open to bond to a carbon on the other side. And this is called a hydroxyl group because it looks a lot like OH ion, which is hydroxide. And that alcohol group or hydroxyl group can bond to any carbon. It can be inside or outside on the chain. It can even be on a branch. The ethers then are very similar to alcohols, but now another carbon chain has bumped the H off from the alcohol. So I remember that there's a carbon at ether end of the oxygen. So the oxygen single bonds to a carbon on each side. So it's named by giving the root name for each carbon chain. So the shorter carbon chain is named first, and then you use the word oxy along with the longer carbon chain. So let's say you had a methyl group on one side and an ethyl group on the other. It would be methyl oxy ethane. And you would write that just as one continuous word. So then the second set of functional groups or families we want to look at is with the aldehyde group. And this is listed as HO, and it's known as the carbonyl group because we put the H first, and I think of it as it hides the alcohol or the OH group, and what it actually is doing is it's breaking up the OH group because we write it HO to show that the carbon is double bonded to the oxygen as well as single bonded to a hydrogen, which leaves space for it to bond to one other carbon. So with an aldehyde, you're going to see a carbon with a double bonded oxygen as well as a hydrogen, and then there's going to be the rest of the R group. So this is going to have to be on an end of the carbon chain in order for an aldehyde to form. Whereas an ether will have to be in the center, and an alcohol can be anywhere. Which brings us to the ketones. A ketone also has a functional group called the carbonyl group because it also has a double bonded oxygen to a carbon, but it's also going to have then a carbon group to each side of it. So when I name this, the oxygen is going to have to be on one of the center, one of the inners. So ethanone is the smallest ketone you can form. Otherwise, there's not a center carbon to put it on. It would be an aldehyde. And as far as naming it, I can just use the length of the carbon chain and then use the ending unknown to show that it's a ketone. And I remember that a ketone, I emphasized the one there with a capital O because there's one oxygen but no hydrogen in ketone. So then the last pair to look at that have some similarities are carboxylic acids and esters. A carboxylic acid has the functional group COOH, and I think of it as caboose, and that's because the COOH is going to have to be on the end of the carbon chain because I have an OH group as well as a double bonded oxygen, which only leaves one bond to connect me to the rest of the stem. So naming carboxylic acids, whatever that stem is, meth, eth, prop, it becomes propanoic acid. You just take the name ic acid to name the carboxylic acids. So an ester group, much like an aldehyde much like a ether bumps off the hydrogen from an alcohol, or ketone bumps off the hydrogen from an aldehyde, an ester is bumping off the hydrogen from a carboxylic acid group. So now I've got another R group here to make this an ester. So this is going to be in the center. I don't have a clever way to remember it except that we've seen this pattern 3 times now, that you have a functional group at the end with hydrogen being the last atom, and now you replace that hydrogen with an R group. So it's formed by combining an alcohol and a carboxylic acid, so it's going to also release a water. Sometimes it's called a condensation or dehydration reaction. And you name it with the prefix for the alcohol given first, followed by the root of the carboxylic acid with ATE as the ending. So alcohol will always be shown to the right of the COOH because that's where the H was removed. So when you look at the formula, if I saw a formula like this, I would know that this ethyl group is my alcohol, whereas the methyl group is my acid. So I would name this ethyl methanoate. So look back at the progression here, and we see that we've got alcohols with an OH group. If you replace that H, then we have an ether. You have an aldehyde with an HO group. If you replace that hydrogen, we end up with a ketone. We have a carboxylic acid with a COOH group, and if you replace that H, we end up with an ester. On the next video then, we will go over Rule 3 and how we put this all together in a name.